We measure the strength of any covalent bond by its bond energy or bond dissociation energy.
Bond energy. I'm guessing that's got nothing to do with how much energy a certain British secret agent has, right?
No, Agent 007 isn't involved in this at all. In chemistry, bond energy is the energy required to break 1 mole of a particular covalent bond in the gaseous state.
Since energy is required to separate the bonded atoms, does that mean the stronger a bond is, the greater its bond energy?
Correct. There's also another parameter called bond length, which measures the bond strength of a covalent bond.
Bond length? What's that?
Bond length or bond distance is defined as the average distance between nuclei of 2 bonded atoms in a molecule. Bond length is inversely related to bond strength.
So the name pretty much explained itself.
Yep. Anyway, here's a table that shows bond energies and bond lengths of some covalent bonds.
From the table, I noticed that the triple bond has the greatest bond energy and the shortest bond length, while the case is just reversed for the single bond.
Nice observation. This is because triple bonds involve more electrons, which exert a stronger attractive force on the nuclei of the bonding atoms, pulling the atoms closer together in turn.
So the greater the force of attraction between the electrons and the nuclei, the shorter the bond length and the stronger the bond.
Exactly. So, by looking at this table, can you compare the reactivity of the 3 covalent molecules?
Sure. A nitrogen molecule has a triple bond. So to break its atoms apart, it takes a lot of energy. That is 944 kilojoules per mole. On the other hand, to break a single bond present in a fluorine molecule, it only takes 158 kilojoules per mole of energy.
So, what does that mean?
It means, out of these 3 molecules, nitrogen is the least reactive, while fluorine is the most reactive.
That's right. Well done. Now, let's look at another table that shows the bond energies and bond lengths of some hydrogen halides.
HCl has the shortest bond length and the highest bond energy, while HI has the longest bond length and the lowest bond energy.
Indeed. Can you tell me the reason for this trend?
In all these molecules, the halogens are bonded to the same element, hydrogen. So, is it somehow related to the size of the halogens?
Yep. For non-metallic atoms like halogens bonded to the same atom, their bond lengths increase down the group due to the increase in their atomic sizes.
So as the bond length increases, the bond energy starts decreasing from HCl to HI.
Exactly. So now can you predict the reactivity of these hydrogen halides?
Sure. HI has the lowest bond energy, meaning less energy is required to break this bond, while HCl has the highest bond energy. So HI is the most reactive and HCl is the least reactive.
Yes, well done. And now that we're familiar with this, let's move on to describing the types of covalent bonds in terms of orbital overlap.
Orbital overlap. Can you explain what that is?
Sure, but first you need to know that each atom that combines has an atomic orbital containing a single unpaired electron. During the formation of covalent bonds, these atomic orbitals overlap so that a combined orbital is formed, containing 2 electrons. We call this combined orbital a molecular orbital.
I see. So, what is the significance of the orbital overlap?
The extent of the overlap of atomic orbitals determines the strength of the covalent bond.
That's cool.
There are 2 types of covalent bonds depending upon the type of the overlapping between the orbitals, the sigma bond and the pi bond.
I see. Let's start with the sigma bond then.
Finding this helpful? We have additional learning resources to offer for Cambridge IGCSE and AS A-level subjects.
Sure. The sigma bond is a covalent bond formed by end-to-end or head-on overlapping of half-filled atomic orbitals along the internuclear axis. the extent of the overlapping is large, and so the bond is quite strong. A sigma bond is possible between the SS, sp, and pp atomic orbitals.
So, teacher, can you give me some examples of sigma bonds?
Sure. Let's start with the hydrogen molecule. In the formation of a hydrogen molecule, the half-filled 1s orbital of one hydrogen atom overlaps with that of the other atom end to end, forming a sigma covalent bond. Similarly, in the formation of an HF molecule, fluorine has an electronic configuration such that one of its p orbital is half-filled. So, this orbital overlaps with the half-filled 1s orbital of the hydrogen atom, forming a sigma bond.
I get it. In the HF molecule, there is an overlap of the s and the p orbitals, right?
Yep. Also, notice that the px and py orbitals of the fluorine atom are completely filled, and so only its pz orbital takes part in the bond formation.
I see.
Lastly, let's look at the fluorine molecule.
Let me try to explain this one, teacher.
Sure, go ahead.
Since a fluorine atom has one half-filled p orbital, when two such atoms come close to each other, the two half-filled p orbitals overlap head-to-head, forming a sigma bond.
Correct. Well done.
Thank you, teacher. So let's move on to the pi bond next.
Sure. The pi bond is another type of covalent bond, which is formed by sideway or lateral overlapping of half-filled p atomic orbitals. The extent of the overlap is small, and hence the pi bond is comparatively weaker than the sigma bond.
I see.
Since the p orbitals are mutually perpendicular, only one of them can overlap along the internuclear axis, and the other two come close to each other from side to overlap. This sideways overlap results in a pi bond formation.
So the overlapping of orbitals must take place perpendicularly to the internuclear axis?
Correct. Also, remember that the pi bond cannot be formed alone. It is only formed when a sigma bond is already present.
Interesting. That must mean that sideways overlapping results in double or triple bonds between the atoms containing 2 or 3 half-filled p orbitals.
Exactly. Also, by the way, a single pi bond is often drawn as two electron clouds, one arising from each lobe of the p orbitals. It should be remembered, though, that the two clouds of electrons in a pi bond represent just one bond, consisting of a total of 2 electrons.
That's a bit complicated, but I think I understood it all, teacher.
Great. Now let's explain the pi bond with reference to an oxygen molecule.
Okay.
The electronic configuration of an oxygen atom reveals that it has 2 half-filled p orbitals, and so it can form 2 covalent bonds. When the half-filled pz orbitals of 2 oxygen atoms overlap along the z-axis, considering the molecular axis as the z-axis, a sigma covalent bond is formed between them. The other 2 half-filled py orbitals of the 2 oxygen atoms overlap laterally to form a pi covalent bond between the oxygen atoms.
Oh, so this is how 2 oxygen atoms are connected by 2 covalent bonds.
Yep. Also remember that the other 2 pairs of electrons present in the 2s and 2px orbitals do not get involved in bonding and remain as lone pairs on the respective oxygen atoms.
Got it, teacher.
Now let's look at the nitrogen molecule to see its pi bond.
Let me try to explain this one. I remember that nitrogen has 3 half-filled p orbitals, so it can form 3 covalent bonds or a triple bond.
Exactly. In the formation of a nitrogen molecule, the half-filled 2pz orbital of each nitrogen atom overlaps with the other end to end, forming a sigma bond. The remaining half-filled 2px and 2py orbitals overlap with those of another nitrogen atom laterally, forming 2 pi bonds.
So a nitrogen molecule has a triple bond, out of which one is a sigma bond and 2 are pi bonds.
Bingo!
Register now for free.